Hello and welcome to our new video. So today's video, we're gonna talk about stored program architecture. So we will discuss on what is stored, what is program architecture, why it is named so. So before starting the actual discussion on stored program architecture, let us do some discussion on punch card computers. So IBM introduced such computers where we used to have punch cards. So what are these punch cards? These punch cards were cards where we needed to make holes to represent data. So in this hole, see there are in the first row we have 1, 2, 3, 4, 5, 6, 7, 8 rows, and using those holes we used to program, we used to give data to the computer. So suppose you want to make a addition operation, so there will be a program, there will be a separate punch card for where we would program, where we make holes, and that punch card will be inserted for loading the program. Then we will have a separate punch card for feeding the data into the computer. Okay, fine. So you can understand that this process is very manual. Again, to see the output, we'll have a different punch card for that also. So in year 1945, scientist John von Neumann, he was a famous mathematician at that time. He introduced an architecture. Before explaining what the architecture is all about, let us dive into the history, how this architecture came. It obviously didn't came out of a blue. So if you have heard about Alan Turing, he gave an idea of a universal Turing machine. Universal Turing machine. So it was made by Alan Turing. Okay. So von Neumann was aware of that machine. So what Alan Turing did in that machine, he thought of a memory where we will store these programs and data. You saw the limitation of punch card, where we need to have separate punch card for a program and data, and there was no concept of memory. Okay, so you have to again make holes on a separate punch card for a separate program, for separate data. So it was not very practical approach. So this universal Turing machine incorporated such ideas. However, it was an abstract mathematical model only, but John von Neumann took the idea from that. Okay, so what he did, we'll discuss it in a few times. So have you heard about Manhattan Project? It is a very famous project, right? So in Second World War, America was trying to build atom bombs, and that project is famously known as Manhattan Project, and this von Neumann was one of the scientists there. Okay, so while working on this Manhattan Project, he realized that they need huge amount of calculations. So there was already a project ongoing, EDVAC project. In this EDVAC project, a stored program architecture concept was already being talked about, and von Neumann contributed there. So in 1945, in a paper named as the first draft report on the EDVAC, he gave this architecture. Now you may ask a question that 1945, why in standing 2021 we are learning the architecture of computer which was given in 1945? It must be very old, right? But believe me, you will be surprised to learn that even in your computer, even this architecture is used mostly. So it was that much of versatile. So that is all about his geniusity of mathematician von Neumann. So what this architecture is all about, let us discuss. See carefully. So we have a central processing unit, right? So what this central processing unit does, it does all the calculations, and inside this central processing unit we have a control unit and an arithmetic logic unit. That is what I discussed in the previous lecture also. Now there is a memory unit. What this memory unit all about? So here in this memory we'll store the programs as well as the data. So program and data will be stored in this a single memory module, and processor through a common system bus will communicate with the memory and fetch those programs and data. So basically in modern day computers also we use more or less the same architecture, of course with some modifications, some a little more sophistication, but the basic idea is same, that we will have a memory unit where program and data will be stored, and processor will fetch those programs and data to make calculations. And we will have input device and output device. So what the input device will do, input device is essentially input those program, those value data into the memory, and processor will take those value memory and output will display that. So this architecture he thought of that in that time, and it was so much, I mean, versatile that we still today we use the same. Now there is a problem. Now the matter is there is a problem. What is the problem? See, suppose a situation arises when you want both program and data at the same time. The problem was with the von Neumann architecture was that the processor could not fetch programs and data simultaneously. What I mean by that, suppose you want to make an addition. Now you have written addition program in a memory. It is already stored there. Now processor fetches that instruction, that program. Now to execute that program, processor needs some kind of data for calculations. But that cannot happen simultaneously. What I mean, if a processor want to take program, he will have to wait until this data transfer finishes, because we are having a common system bus for program and data. So until this transfer finishes, processor cannot fetch data. So the bandwidth is very less. The latency is bad and the bandwidth is very less. Because one more thing, that memory units are very slow. They are slow devices. Why slow? Because processor works in gigahertz. Processor are very fast. They work in gigahertz, right? And memory work in megahertz. In modern day processor also, the processor works in gigahertz and memory unit works in megahertz. So the execution, so the whole process of fetching the instruction, fetching the data is limited by this, data transfer rate. So being a very slow data transfer rate, because memory cannot respond to requests simultaneously, you have to make one request, then you have to wait, and then you have to again make another request when the memory unit is free for us, again a data transfer, then you have to. So you can understand that one by one you can do these things, so you cannot do parallelly, right? Okay, so that is called the bottleneck situation of von Neumann architecture. So what is the bottleneck situation of von Neumann architecture? It is that fetching of instruction and data simultaneously is not possible. And that is a big problem because processor cannot operate to its full capacity because of these limitations of data transfer. So you have to if suppose imagine if you could bring program data together, then you can start execution at just right after them. But suppose you fetch the program, then you have to wait, then data would come again, then you can only start this execution. So what are the solution of this problem? There are many approaches that we can do. One modern approaches is using cache memory. In COA subject, we will learn cache memory in detail in the upcoming lectures. So what happens in cache memory? In cache memory, we have a intermediate memory in between the memory unit and central processing unit. So this cache memory will store recently accessed things, and as the speed of cache memory is very high, so this bandwidth related issue is solved very much. So the second solution is multi-threading. What is multi-threading? Multi-threading is basically managing multiple requests in separate threads. So managing multiple requests in separate threads. What I mean by that, just imagine if the memory unit could respond to multiple requests at the same time. If memory unit could respond to multiple requests at the same time, then this problem could be easily solved, right? Suppose memory unit could respond to program as well as data requests, so they can be given to the processor at the same time, but that doesn't happen actually. But in general that doesn't happen, but using multi-threading you can do that thing as well. One more approach is to use DDR SDRAM, which we actually use these days. So DDR, have you heard about DDR1, DDR2, DDR3 RAMs? You definitely have heard about this. So what is DDR? DDR is double data rate, and SDRAM stands for synchronous dynamic random access memory. So in DDR SDRAM, use the when there is a falling edge, we can respond to a separate request. When is a rising edge of a clock cycle, we can respond to a separate request. So we are not discussing these things in detail. There are one more approach that can be incorporated, that is PIM, which is processing in memory. So inside memory unit you build a processor. So in memory unit you can do processing, and that can also mitigate that problem. One common solution that was given at that time was by the introduction of Harvard architecture. So what Harvard architecture did, they used a separate instruction memory and data memory. So instructions means the program will be stored here in an instruction memory, and data will be stored here. Okay, so the control unit can send a program request and a data request, and they can be brought in the same time. So this bandwidth issue is very much solved in Harvard architecture. But the problem is that in reality we don't implement this purely Harvard architecture. Why? Because there is some problem. Have you heard about 2 RAM in your system? You have definitely heard. Have you heard that we have a instruction RAM and we have a data RAM in your computer? You definitely have a single RAM even in your computer, in a smartphone, and everywhere. Because we are essentially using that decade-old von Neumann architecture, right? Yes. So even though Harvard architecture has a lot of improvement over von Neumann architecture, but in reality this Harvard architecture is not very much used, at least on the main memory system. Yes, they are used, I will tell you about that, but at least in main memory system, this Harvard architecture is rarely used. Okay, so after telling you this, let us come to what modified Harvard architecture. So in reality, in the computer that you are using, the mobile phone that you are using uses some kind of modified Harvard architecture. So modified Harvard architecture is like it borrows the quality of both the architecture. Okay. So von Neumann architecture had some advantages, that it was very simple, whereas Harvard architect, but the bandwidth was an issue, whereas in Harvard architecture the bandwidth is very high. So what happened actually, that this is main memory, okay, this is main memory, and in between CPU and main memory we have a cache memory. So this cache memory can be split into two sections. One is instruction memory and other is data memory. Okay. Now, for your information, let me tell you that have you heard about L1 cache, L2 cache, L3 cache? This L1 stands for level 1, this L2 stands for level 2, and this L3 stands for level 3. Don't be too much intimidated by these terms. Just for your information, that this cache splitting is done in L1 cache. When we learn about cache memory in detail, we will talk about this. So L1 cache is splitted in I cache plus D cache. Means I cache for instruction cache and D cache for data cache. So cache memory is like storing the recently accessed things. Okay, so if you store recently accessed instruction and data and you prefetch them already, then CPU won't be accessing those from main memory. They will be taken directly from the cache memory. So that bandwidth issue is solved. However, you have a unified main memory, and this main memory will be of bigger size to hold all of your instructions and data together. And this cache memory will be a very small size memory, and it is very fast. And this L1 cache is usually on chip cache. It is usually fabricated inside the CPU. So this cache is inside CPU and it is very low size, 64 KB or 128 KB. It's like that. Okay, so by split cache architecture, we can mitigate this problem very much. When we discuss about cache memory, you can understand better why split cache architecture solves the problem. So what we have learned today, we learned that the punch card, how punch card was so tiring. So the problem of punch card technology. Then we had von Neumann architecture. John von Neumann proposed this architecture, that we will have a single memory module where this data and program will be located and stored, and in the single memory, from that single memory, central processing unit will fetch those programs and data. Okay, now why it is called stored program architecture? You may ask that question, right? This is because programs are stored in memory. Earlier we used to feed program, okay, but here we can store those program and even we can modify that program. So that is very flexible approach. Before this stored program architecture, we had fixed program architecture. Like suppose you have a calculator in your home and you can do specific tasks, that is because it is an embedded system, so you cannot change the programming of the calculator usually. Okay, so that is fixed program concept, whereas in stored program concept, the program is stored in memory and you can modify that as well. That is called stored program concept. Okay, fine. So in the next video, we'll learn about different type of CPU registers. I told you in the previous video that we have CPU register, some are general purpose, some are special purpose register. We'll talk about them, how they work, what are their functionality, how they communicate, where they are useful, and those things in the upcoming lecture. So keep learning. Goodbye.